Today we are going to discuss about the SRN1 mechanism, followed by the factors that will affect the rate in case of aromatic nucleophilic substitution reactions and some name reaction of this particular chapter. So before starting SRN1 mechanism, as you know that we have completed our three mechanisms. These are ARSN1, ARSN2 and the benzene mechanism. So yesterday we completed the benzene mechanism, and in benzene mechanism we know that there are some factors, that is the group which is already present on the benzene ring, that group will direct the formation of the benzene. So for that I have a question. For example, we are having this benzene ring and this OCS3 group is attached with that one, and we have this one, that is metabromoanisole, and similarly we are having orthobromoanisole, right? So this is your orthobromoanisole. When both are subjected to undergo the benzene mechanism, means both are subjected to react with soda amide NaNH2 in liquid ammonia, at that time they will produce the same product. So this is another indication, this is an evidence that prove that this particular reaction is proceeding with benzene mechanism. And how we can explain it? Yesterday I told you that when OCS3 group is attached and a benzene was synthesized, at that time I told you that which one will be the major product and which one will be the minor product, because it stabilizes the carbon ion which is formed in the second step of the NH2 negative attack, that is a nucleophilic attack. So when we compare these two, for example this is your one substrate and this is your another substrate, when we compare these two substrates we can clearly see that this bromine will be eliminated out from here and this bromine will be eliminated from this place. So in this case, means in case of orthobromoanisole, you will get a single benzene only, there is no other possibility. So this benzene will be synthesized. But on the same side, if we compare this particular substrate, at that time we can see that because this is the bromine and this is the ortho position and this is also the ortho position, so hydrogen can be eliminated from both the positions. So in this case we have two possibilities of benzene formation. Now which benzene will be synthesized, that will again be determined by the presence of this group, and after formation of the benzene which group will it attack, which position will the nucleophile will attack, that will also be determined by the group which is already present on the benzene ring. So in this case I will show you that how it is affecting. So first of all I will show you the two possibilities of benzene formation, how the benzene can be synthesized on this particular substrate, and when we observe it we can see that one, this benzene can be synthesized and this benzene can also be synthesized. Now we know that here OCS3 group is present and here OCS3 group is present, and this group is electron withdrawing in its nature, right? So as you know that the first step is the attack of NH2 negative on the this one, hydrogen will be eliminated out, right? So hydrogen can be eliminated from this place, or it can be eliminated from this place. Now from which it will be eliminated out, that is the point. So the hydrogen will be eliminated from this place, and this will be the benzene which will be synthesized during this particular process. And you know that when the benzene is same in both the substrate, at that time the same product will be synthesized by the attack of NH2 negative on the second step, right? So that's why we can see that if we are having metabromoanisole and if we are having orthobromoanisole, when both are subjected to react with soda amide in presence of liquid ammonia, the main product will be, determined by the presence of OCS3 group, and the main product will be meta-anisidine. So in both the cases, this will be the main product, that is OCS3, and to meta position there is presence of NH2 group. So it will be the main product, and the reason behind that is because both substrates are proceeding with the same benzene, right? So that's all about the benzene mechanism. So now we are coming with our next mechanism, and this mechanism is SRN1 mechanism, and this mechanism is simply called as the substitution radical nucleophilic unimolecular mechanism. When we talk about this mechanism, actually the possibility of this kind of mechanism is also less, and this mechanism was discovered accidentally, right? As far as the chemistry is concerned, as far as the mechanism is concerned, it generally proceed with single electron transfer. Means, as the word radical is here in this particular mechanism, means it will be initiated by some initiator, and then the reaction will propagate, and finally the reaction will be terminated. So this mechanism proceed with single electron transfer mechanism, SEP mechanism, and this is called SRN1 mechanism. The overall mechanism is being displayed on this screen, that first of all initiation will happen with electron donor. This electron will come, and this is your substrate having leaving group will get converted into a radical anion. After formation of this radical anion, this will, X negative will be eliminated from this substrate, and this will get converted into AR radical phenyl radical. Now this phenyl radical will now react with the nucleophile, the Y negative, and will get again converted into radical anion. After this radical anion formation, it will come in contact with the substrate, that this was your substrate, so it will again come in contact with the substrate, and this substrate will now get converted into radical anion, and the product will be isolated, right? And overall we can see that this is the substrate, this is the nucleophile. When substrate and nucleophile react with one another through single electron transfer mechanism, SRN1 mechanism, at that time we can see that this product will be synthesized and leaving behind the X negative, the leaving group. When we schematically represent it by drawing the benzene ring as well, we can see that this is your substrate, this is your first substrate, which first of all will accept the electron from initiator, that will initiate the reaction with single electron transfer mechanism and will get converted into the radical anion. After formation of this radical anion, the radical anion will get converted into this particular radical, right? This is third, you can see it here, that it will give rise to aryl radical. So this is your aryl radical in which the X negative will be eliminated out, right? And this radical now react with the nucleophile, this is your nucleophile, and will get converted into 5, that is again the radical anion, and this 5 react with this particular substrate and again regenerate this one, that is radical anion, and this is your product that have been eliminated during the course of reaction. So this is the overall mechanism that we can represent, that single electron transfer mechanism is here. Now how this mechanism was observed accidentally, I want to show you a reaction. This is the reaction on your screen and you can see it, that this is the 5-iodo 1,2,4 trimethyl benzene, right? When it is subjected to react with KNH2 in presence of liquid ammonia, it will give rise to this product, as well as this product was also synthesized, right? And when we compare the ratio of these two products, the ratio came out to be 0.63 raised to 1, right? This is 0.63 raised to 1, means from this particular substrate we are getting this product as well as this product. When the same reaction was carried out by taking a different substrate, and that substrate was 6-iodo, right? 6-iodo was now taken, and at that time again you are getting these two products, but the ratio of these two products were now different, right? And the ratio of this particular reaction came out to be 5.9 raised to 1. So if we compare that the mechanism is allowed to proceed via benzene, at that time you will get this particular benzene, right? There is no other possibility. In both the cases you will get only a single benzene. So the proportion, the ratio of both the products in both the reaction will be same at that time, but it is not same. It means the reaction is not proceeding with benzene mechanism. Instead it is proceeding now with some different mechanism in which the ratios of the two products in both the conditions are different, right? So in this case you are getting this type of radical, right? And in this case you are getting this type of radical. So we generally estimated that the mechanism is not a simple benzene mechanism. The mechanism is somewhat different as comparison to the benzene or the arine mechanism we discussed earlier. So this is now proceeding with SRN1 mechanism, and mechanism I have already told you about this one. And now this is another example of this SRN1 mechanism, that is symmetric as well as asymmetric biaryls can also be synthesized by using this type of mechanism. So this is another case in which the same mechanism has been observed, the SRN1 mechanism. Now after discussing the four mechanisms of aromatic nucleophilic substitution reaction, now the time comes to explain the different type of factors that will affect the rate of aromatic nucleophilic substitution reaction. And when we compare it, there are some categories that particularly affect it. So first of all we will tell you about the substituents which are attached on the benzene ring and its effect on the aromatic nucleophilic substitution reaction. So you have seen a trend actually, that when electron withdrawing groups are attached, at that time the rate of aromatic nucleophilic substitution reaction will be fast. So here is a example that in this particular reaction, in this particular substrate, you are having 3 NO2 group which are electron withdrawing groups. Here you are having only 2 NO2 group, and here is you are having only 1 electron withdrawing group. So the rate of reaction will be slowest in this case and fastest in this case, because 3 electron withdrawing groups are here, because we are eliminating a particular group, a particular leaving group, right? And a nucleophile is going to attack on the benzene ring. So the condition for that, then how a nucleophile will attack on the benzene ring? The benzene ring should be electron deficient, right? So at that time, if we attach different electron withdrawing groups to that one, it will enhance the rate of reaction. So this is the first factor that will affect the rate of aromatic nucleophilic substitution reaction. The second effect, the second point which we should be clear in our mind, that the effect of leaving group. When we say about the effect of leaving group, just go to first lecture in which I was telling you about fluorine, chlorine, bromine and iodine. When we were discussing about it, you know that this is a case where fluorine is attached, and this is a case where chlorine, bromine and iodine is attached, and you can see the difference in the rate of reaction, that this particular reaction is 300 times faster as comparison to this particular reaction. But when we compare these three, the rate of reaction is almost constant in this case, and no large difference between these two cases and this particular case. It means we can say that here in this case the fluorine will stabilize the intermediate that have been synthesized, and secondly it also suggests that the rate of this particular reaction and this one is this is almost same, and this is, I think, almost it is not same, but the difference is not very big. So from here we can clearly say that this particular carbon and the leaving group bond has not been broken in redetermining step, right? So means this is particularly stabilizing the intermediate, and that's why the rate of reaction is very faster in that case, right? And when we compare this one from this particular point, we can conclude that this particular carbon and halogen bond is not being broken in redetermining step. So if we compare the effect of leaving group on the rate of aromatic nucleophilic substitution reaction, so if we have some leaving group trend, at that time we can say that fluorine will be the best leaving group during the aromatic nucleophilic substitution reaction, followed by NO2, then tosylate group is here, then SOPH group is here, then chlorine, bromine, iodine, and different groups like this one. So this is the pattern for leaving group. Now this is the effect of substitution pattern, means we have already told you that electron withdrawing group, when they are attached on the benzene ring, they will increase the rate of aromatic nucleophilic substitution reaction, but there is a condition that the electron withdrawing group should be positioned either at ortho or para with respect to the leaving group. When it is attached at the meta position, it will not increase the rate of reaction. For example, here you can see that this is your para-fluoro-nitrobenzene and this is your meta-fluoro-nitrobenzene. When we compare the rate of these two reactions in aromatic nucleophilic substitution case, we can clearly see that this reaction is fast as comparison to this reaction. However, the distance between this electron withdrawing group and this particular fluorine is less as comparison to this one, but this is the case that when NO2 group or any electron withdrawing group, when attached at ortho position and para position with respect to the leaving group, they will increase the rate of aromatic nucleophilic substitution reaction as comparison to the position meta to the leaving group, right? So this is the effect of the substitution pattern on the aromatic nucleophilic substitution reaction. So these are the three categories if I'm particularly talking about the factors that will affect the rate of reaction in aromatic nucleophilic substitution 1. Now we will come to the name reaction of this particular chapter, and the first name reaction of this particular chapter is the von Richter rearrangement reaction, and this is discovered in 1871 by the scientist Victor von Richter, right? After this discovery, what is the reaction? What is this particular reaction? This particular reaction is all about the reaction between aromatic nitro compound with Cn negative, in which there will be a sign substitution, means there will be a attachment of carboxylic acid group ortho to the nitro group. So this is a case of sign substitution reaction, right? What will be the mechanism of this reaction? That this is a particular aromatic nitro compound and it will react with KCN in ethanolic solution of this particular KCN and will get converted into this particular product. Means this is your NO2 group, it is positioned here, and the carboxylic acid group will attach itself to this position. So this is the case of sign substitution. When we see the mechanism of this particular reaction, it will proceed with the nucleophilic substitution manner. So the first point, the first step of this reaction is the reaction of this particular Cn negative at this position, right? So when this Cn will attack at this particular position, you can see that first of all, when it is going to attack here, there is a moment of this particular carbon-carbon multiple bond to this nitrogen with the movement of electron from here to oxygen. So in the second step, you can clearly see that this is a double bond between this carbon and this nitrogen, and when there is a double bond between this two position, carbon and nitrogen, here the attachment of Cn group is here, and finally, because the aromaticity of this particular ring is being lost in the first step, so it will regain the aromaticity by leaving this particular H positive. So H positive will be eliminated out from here and it will regain its aromaticity, right? So Cn will be attached at ortho position with respect to this NO2 group. Now you can see that in the next step, when there is formation of this, you can see that this is nitrogen, and to this nitrogen two oxygens are attached and both are carrying the negative charge, and this particular Cn group is here. So nitrogen and carbon both are here. Nitrogen is more electronegative as comparison to this one, so this particular carbon is electron deficient and bear a partial positive charge, and when nitrogen is being attached with this particular carbon, this oxygen with its electron pair will now attack on this particular carbon with movement of electron from C triple bond N to nitrogen, right? So we can see that there is a formation of this is your 1, 2, 3, 4 and 5. There is formation of a 5-membered ring, right? Now there is another attachment, that this particular bond, that is O negative, it will move to form N double bond O with migration of this particular bond, that is N oxygen, to form C double bond O NH2. Here it will abstract, means when this particular electron will move towards this one, it will abstract H positive and will get converted into NH2. So remember this particular intermediate during the course of reaction. It will help you when we investigate the evidences about this particular mechanism. So remember this particular intermediate, and after formation of this one, now there will be a formation of nitrogen bond, and this nitrogen along with its lone pair of electron will now attack on this particular nitrogen with elimination of water molecule from here, that is hydrogen from here and oxygen from here. So there is attachment. This is particularly two-step mechanism, and it is completed in one step. So water molecule will be eliminated, nitrogen will attack on this particular nitrogen, and there is formation of nitrogen bond between these two nitrogens, right? Now the OH negative will attack on this particular carbon, and movement of this electron will take place, and there is formation of CO negative OH. Finally, there is a movement of this particular O negative to form C double bond O with movement of this electron to form N triple bond A N, and movement of this electron to form C negative, right? So this will be synthesized, and finally this C negative will abstract H positive, will take H positive from the solvent and will get converted into the substituted carboxylic acid, the substituted benzoic acid. So this is the overall mechanism of the reaction that I was talking about. This is the von Richter rearrangement reaction. So this is a case of sign substitution reaction, and generally this reaction happen in case of aromatic nitro compounds, right? And aromatic nitro compounds react with the nucleophile Cn negative and will get converted into substituted benzoic acid. Now when we talk about the evidences about this reaction, what are the evidences that prove that reaction is really proceeding with the said mechanism, with the given mechanism? So you can clearly see here that nitrogen is being eliminated out. For example, this is the place from where nitrogen was eliminated, right? So when we observe the product, so it was found that N2 is the major product of this particular reaction. An indication of this N2, isolation of this N2, formation of this N2 is an indication that there is a formation of nitrogen bond during the course of reaction. So this step is really possible in that case, that this is the nitrogen and this is the nitrogen, and both will react and form nitrogen bond. Second, I was telling you about this particular species, that this particular intermediate can be isolated, it can be prepared independently, and when it is subjected to the same condition, it will give you this product, that is the von Richter rearrangement product. So this is another strong evidence regarding this mechanism. When we are particularly concerned about the reaction, you can see that here there is formation of C negative, that is this particular phenyl ring is having negative charge, right? And it is abstracting H positive from the reaction condition from the solvent. When this particular reaction is being carried out by using deuterium, for example, if it is being carried out by using D2O and C2H5OD at that time, here at this particular position hydrogen will not come, instead there will be appearance of deuterium at this particular position. So appearance of deuterium at this particular position is an indication that this particular C negative will be synthesized during the course of reaction. So this is again a very strong evidence that prove that this particular species has been synthesized during von Richter rearrangement reaction. Similarly, another evidence that prove that this particular reaction is proceeding with the said mechanism is that when oxygen of water, for example, we are having C2H5OH and we are having water. When oxygen of water is being labeled 18 oxygen, we have taken water with 18 oxygen labeled, at that time we can see that because the product is containing two oxygen, that is one oxygen is carbonyl oxygen and another oxygen is OH oxygen, so half of the oxygen of the product will be labeled. It means when we talk about this particular point, you can see it that this is the point, that this particular oxygen C, when O negative attack at this one, it form C oxygen, means one oxygen is being supplied by the NO2 group, whereas the other oxygen is being supplied by the solvent, right? That's why the half of the oxygen is labeled and another half of the oxygen is not labeled, because that oxygen is supplied by the NO2 group which is already present on the aromatic system. So these are the overall evidences which proves that reaction proceed with the said mechanism. So that's all about the von Richter rearrangement reaction and SRN1 mechanism. Tomorrow we will discuss some more name reactions of this aromatic nucleophilic substitution reaction.